Hello, APPCAIR seminars. So today, Professor Goel would be talking on a generalized multimodal deep learning model for early crop yield prediction. Over to you, Professor Poonam Goel.
Okay, can you see my slides?
Yes, we can.
No, just a minute. Something. Where is that? Where are the presentation slides? Yes. Okay, so I'll be talking about a multimodal deep learning model for early crop yield prediction using histograms. So this paper was published in IEEE Big Data in 2022 December, and this is our first work on satellite satellite imaging, that is Earth of, yeah. So after this, we have also one more paper is published, which is on numerical data on crop yield prediction, and we are also working on two more problems on Earth observation in the area of fire prediction and the crop yield prediction. Okay. So coming to the overview of presentation, some motivation, data preparation and augmentation, model architecture I'll be talking about them, then contributions and results. So why do we do crop yield prediction? First of all, so it enables farmers to know yields across their farms well before the harvest for better management, so that they can manage they can plan where to store, how to sell out the harvest, and how the whole management can be planned. And it is required to know beforehand for governments, like for deciding MSP, and which is and export import policy, for better warehouse management, and insurance premiums for the farmers. And how and what is the crop yield prediction, and how can we model it? So in the literature, it is modeled in various ways, as is static data, the whole year, meteorological data as static, and some people have taken as time series data. So we have modeled it as multivariate time series data as the basic model, and then we have incorporated the different kind of modalities into the system. So it is a agrometeorological data we have used, and we have also used image data captured by satellites. So basically the idea of this study was that to find out how the recently launched satellite work for crop yield prediction. So, and whether they can predict as accurately as numerical data was predicting for crop yield, and since the recently launched satellite were high resolution data. I mean, the images were high resolution, spatial resolution, but the challenge was the historical data was not available. So lack of training data is there. Lack of training data is there, and because the recently launched satellites are launched in 2014 and 2015, Landsat and Sentinel respectively, I guess. And so we have only 5 years or 7 years data. Because the crop yield data, so the yield, the total yield in a region is not available for, very recently available years. So we have used this kind of data, yield data, which is yearly. So we have assumed that a crop is actually harvested once in a year. If it is like two times in a year, like for example winter wheat and spring wheat, so we treat them as two different wheats. So it is a yearly data. So in every region, we have considered US county regions and India district level regions. So count for each county, the how much yield happened in a year, that is your yield data. Similarly, for the district of India. Surface reflectance band data, that is the image, satellite image data, which is in time series. We take this in the form of histograms. Why we will see, because the image, these satellites are high resolution satellite image they give. So the time series of high resolution images is very difficult to process due to its you know memory requirements. So we have converted the images in histograms. Why histograms will work, we'll see. So we have considered MODIS, Landsat 8 and Sentinel-2 from Google Earth Engine, the whole data. And soil data we have also considered, which is static, which is also taken from the satellite imaging. So these are also converted in the form of histogram. So these are like clay content, bulk density, pH in water, water content, carbon, sand content. So 6 different um, factors, and for each factor you have satellite images at 6 different depth levels. So depth levels, the below the surface, so at surface 10 centimeter, below the surface 30 centimeter, and so on. So this is a depth level data is available. So meteorological data, which is in time series and which is a numeric data. So 12 attributes of numeric data we have captured at the temporal resolution of 1 day. Every day this data is available, so we can capture that, and later we have aggregated this data to match with the data of the satellite temporal granularity. So the type of data which is used in literature is vegetation index, image, histogram. So vegetation index like NDVI, NDWI, EVI, that is the normalized difference vegetation index, water index, and enhanced vegetation index, etc. There are many others. So these are derived from mainly these 4 bands: red, green, blue, and near infrared bands. So these vegetation indexes are available and easy to download from Google's Earth Engine, because this data is very compact, and you can have one value for a county for a time stamp. So this is very small data which we can handle easily, but do not capture the reflectance band data in fullest. So we did not consider vegetation index. Image data, as I told you, is very large and very difficult to store, but complete information is there, all the bands and each county data you can actually download the image, right? And histogram data, so we convert the image data. So it's not that we are downloading images and then converting. This Google's Earth Engine allows us to, capture data in the form of histograms. So we capture the histograms directly. We have to write a code for that, but that is easier to handle because you get the data in the form of histograms. So number of pixel against the range of intensity values for a band, um, that is one bin, and this will not actually lose any information because this has a property of permutation invariance. So because the crop yield prediction is a problem where the location of a pixel is not important in a county, right? So wherever it is there, it will be contributed in the same way, the intensity value. So the small, approximation is involved because you are making a bin of a range. So all those values will be, converted to in a bin, right? So number of healthy uh, crop pixels contribute to the crop yield of a field. Okay, so we will not lose information to predict the crop yield. So we have to prepare our data before we push it into the architecture. So there is a histogram generation, we have to do it, handling missing values, because when we download data from the image, then we have to do there will be many pixels where the values will be missing for different bands. So these missing values are to be handled. So we estimate them using linear interpolation. And meteorological data, again missing values are handled with the forward fill method, and these are captured daily granularity and aggregated to match the temporal granularity of the satellite data. So different satellite, they have different spatial resolution and different temporal resolution. For example, MODIS has temporal resolution of 8 days, whereas I think Landsat has 10 and Sentinel 16, or maybe Sentinel 10 and Landsat 18. I forgot, right? And processing meteorological data, sorry, this I have done, completed. Then padded crop cycle we have used. So this we have given, we have used, I mean, people have not used, I think, padded crop cycle. They have used crop cycle. So crop cycle is the sowing time to the harvest time. But we have uh, padded with the 2 timestamps before and after that cycle, so that we can capture any kind of anomaly, sudden change in climate condition, and the variation in sowing and harvesting, that all will be covered if we use padded crop cycle. So in our work, we generated histograms. So we have surface reflectance data for a bigger region. For example, the region is like a state or maybe country or maybe a very large region. Then we have to filter data according to the location. And the location, you apply the cloud mask. If there is a cloud, so you have to apply the cloud mask to get the actual data. So if the cloud information is beyond some threshold, then you have to, estimate that value. But luckily, these are already done by earlier researchers, and we use, built-in functions for these. Surface reflectance histogram generation, we do similarly, we do soil attribute histogram generation. So for all soil properties, we need to generate the histograms. So we stack these soil properties one over the other, and then volume is created. So the depth of the volume is different factors of the soil, because soil is not a temporal data. For entire year, you take the same soil information. Not entire year, maybe a number of years you take this soil, information same. So it doesn't change that frequently. So the whole stack is the volume, and you have histograms for different locations in as columns, and depth is the different factors. And then you apply these two along with the meteorological data, which is a numerical vector kind of data, but which is time series data. So we have different type of data. One is histogram time series data, numerical data, which is also time series, but the soil data, which is static, but it has depth information. So at each depth, I think I'm sorry. The columns in soil attributes the different factors, and the depth is the depth of the soil depth. So since the data available is very less, 5 years for I think Sentinel and 7 years for Landsat, and 2 years we keep for testing, and remaining years we keep for training. So for one, it is 5 years training data, and for other, it is only 3 years training data. So data is very, very less, and we know that the deep learning models, they need larger amount of data to train well. So we have proposed two data augmentation techniques. One is the inverting time series and temporal irregularity. Inverting time series is generated new training samples. So we reverse the order of the time series, and the target value will remain same for the same county and for the same year. And temporal irregularity, we drop 10% of the time stems from the time series and create another time series, and the target value remains the same. And so this 10% is randomly chosen time stamps. So in every time series you get the different missing time stamps. So overall architecture is as follows: that you have surface reflectance encoder SRE, then you have soil data encoder SDE, and you have core temporal module CTM as the LSTM sequence, and you have DSM, that is depth soil modeling module. So that actually allows you to select the soil feature at a particular depth. So we'll see that in detail. So this is the overall architecture of the model. So the first one is the surface reflectance encoder. So here the surface reflectance data time series is in columns. B is the bins here. B is the bins, and D is the depth, that those are the bands. So if Sentinel has 12 bands, so it is 12 band, 12 depth, right? So you apply convolution, 1D convolution. Here mistakenly 2D convolution in this picture is written, but it is 1D convolution because the columns are different time stems. So we cannot convolve across the time stems, right? So 1D convolution is applied on the whole depth as usual, and then max pool 2 into 1 size max pool is applied, and 3 layers of convolution is applied, then linear layer. So simple encoder, and then you have soil data encoder. So you get soil as the volume, where the attributes are as columns, bins on the rows, and depth is the depth of the soil. And this again, it has a 1D convolution, 3 layers of 1D convolution and dropout, and you get the encoded embeddings of soil. And these are applied to our core temporal module. Core temporal module, as I described, it is a sequence of LSTM, and where the meteorological data is also applied, and layer normalization, linear layers, two linear layers are applied, and then regression to get the crop yield. And here DSM at each time stamp is applied. So what is DSM? We'll see. So depth level selection module of the soil attribute is the DSM module. So what it does, it selects depth for each attribute. So at a time stamp, when you when in the first week or the second week of the after sowing the crop, you need only 1 centimeter of the information. So maybe that is required, and after say 4 weeks, this little deeper roots goes. So you need attributes at a little later depth. So this is the first time we have introduced the depth level selection of the soil information to our module. This is, I told you, CTM, that is core temporal module, and this is the whole architecture which is applied. And contrastive loss is used to so the contrastive learning also work as the data augmentation technique. You can think in that way also, because you make the positive pairs and rest are negative pairs, so one is compared with all other instances in the batch. So those many instances, so it manifold, it increases the data. So we have applied the contrastive learning, and that helps a lot in in learning part of our module. So we have used batch wise and pair contrastive loss. One is compared with all other in the batch, and the mean squared error is used. And this contrastive loss is used for both soil and for the surface reflectance data. So CL1 is for surface reflectance, and CL2 is for the soil, and MSE, which is mean squared error of the crop yield. So the contribution to this is we have incorporated information from different modalities, phenological characteristics of a crop, that in the form of surface reflectance data, soil properties, meteorological conditions. Integrated time series with the static data. So here two time series with one numeric, one histograms, and the soil properties as static data. We applied data augmentation and contrastive learning to handle data scarcity, and the proposed generalized model performs equally good across crops and regions. In-season prediction is also very impressive. So we'll see the experimental results. So here RMSE is given in unit of bushel per acre, and crop yield network CYN, which is the name of our network, and its variance with yearly and padded crop cycle is compared. So if you use yearly information, if you use the padded crop cycle information, you can see there's a slight change in the result, and it is better for padded crop cycle for all across all satellites and crops and regions. So these are different models which are used for crop yield prediction in the literature, and you can see that MODIS, Landsat, and Sentinel for US data BCYN is our baseline crop yield network, which is not having um, the depth selection module and contrastive learning, right? So this is a baseline. We have results for without, contrastive learning, but with DSM and other combination, but here it is not shown. So gradually, when we increase each of our module, it improves. So you can see that best results are obtained by CYN in um, both the crops, corn and soybean, US and India. Then we have results with the data augmentation. So data augmentation actually improves the results a lot. From 21 of MODIS, we have uh, so MODIS we couldn't improve, but Lancet and Sentinel from 21.819 to 18.587, which is 14.81% improvement, and 15.67 improvement for Sentinel. This is in US data. Yield is, I guess, corn. And India, the corn results, the best are achieved when both data augmentation techniques are applied. Only inverse time series is applied. It is from 14.85 to 11.36. Only temporal irregularity is applied, then it is similar. A slight difference. Slightly, I think inverse temporal time series is working better. But if when you apply both, you get better results in, uh, you know. So in India, it is for one Sentinel, it is the best, which is 23.72 percentage improvement over the no data augmentation. And this is in season prediction. In season prediction, you can see that um, ours is here down, and all other existing models are here. So in season prediction, if you go back in, I mean, if 5 timestamps before you predict, then this is, almost same as the end season prediction. So end season prediction is this, and CYN 11.328 is the end season prediction. 5 timestamp before is 11.409. 4 timestamps before is this. So it is slight change only in season prediction. Similar results for soybean also. This is multi-crop training. So we checked the generalization capability of our model. So we trained our model on multiple crops. So the data for 2 crops were available: soybean and corn. So we trained on that, and then predicted for one crop for US and same as for India. So the error RMSE, increased a bit, because RMSE would increase if you will be training your model on two different crops. There, many things will be different, but we have chosen these 2 crops because their at least time, the crop cycle is similar. So we have taken the overall times, cycle of both the crops. So it is lengthier than the single crop. So these errors are a bit higher than what we achieved with the single crop training and prediction for the same crop, but not, uh, you know, not too bad as other models are performing. They are far better than the existing models. So if you go back, then you can see it is like, this is for India, I guess. If you see, it is for US, it is 18 point. So the best is 18.587, right? And in multi-crop training, it is, you are getting with Lancet these, so which is close. So we also, so here the bin size, the bin numbers are taken 64 in all the experiments. Though we experimented for various bin sizes, and we found that as we increase the number of bins, our results improves, and but the improvement is little after 64, 128, 256 we tried. That is, the improvement is little, but the convergence of the model is faster, is much faster. So you need half of the epochs only if you take larger number of bins. But maximum improvement we achieved from 32 bins to 64. So we have chosen 64 for all the experiments. So highlights of our work is, this is first attempt to use the modern advancements in representation learning methods for crop yield prediction. It addresses the problem of data scarcity with surfaces when using data from recently launched satellites, and the positive impact of data augmentation in time series of surface reflecting data is observed, and cross crop and cross region training results highlight the superior generalizing capability of CYN, and the maximum the best actually RMSE achieved by CYN for corn and soybean are 11.328 and 5.99 for US, and this is, I guess, is the best with 5 years, 3 and 5 years training data. Slightly better results are obtained in the literature with the 20 years or more. So that is our next paper, which is published with numerical data, where we had 20 years or maybe 24 years of data, not satellite numerical data. We are achieving little better than 5.99 of soybean. So these are the results. I think that's all from my side. If you have questions, please feel free to ask.
Thank you for the interesting talk, Professor. So I have a couple of questions. So is
Yeah, sure, please.
so you mentioned that just sorry, just a moment. There's some slight overhead.
Sorry.
Just give me a moment. There's a flight overhead. There's some noise here.
Okay, okay, sure.
Yeah. So in one of the slides, you mentioned that you use some sort of augmentation.
Data
What exactly?
augmentation. So
Uh,
data augmentation, since we are using, I think, around 600 counties of US and around roughly same number of districts from India separately, right? And so 600 counties, only 3 years data or 5 years data we have for training. That means for each county, you have only 3 instances or 5 instances of the same crop.
Yes.
So this data was very less for training, deep learning models, and that's why we stick to LSTM only. Otherwise, we could have used the, more complex architectures. Not possible with this much of data. So the time series which we have from sowing week 2. So this is mostly the temporal granularity is, for example, for modest it is 8 days. So the sowing first time stamp is 0 to say t and nth time, right? So of the crop cycle, suppose a 6 months crop cycle, so those many time stamps you will get in the time series. Now, what we did, we reversed the time series. So we now have, if you have time series TS1, now we have TS1 dash, which is TN to T1.
Got it. Got it. Okay. So these things you have discussed on other slides. I thought, and I was wondering what that data augmentation could be. Yeah.
Yeah.
Yeah. Yeah. Okay. So,
And yeah.
sorry. Yeah. Please go ahead.
No, only I was talking about the temporal irregularity where we dropped some of the timestamps. So
Yeah.
if it is say 30 timestamps, 10% of that we dropped and we created another time series, say TS dash dash.
Got it. So another question I have is, so the idea of using histograms as a signature of the percentage of yield is, I mean, interesting. So for what kind of crops does this work? I mean, so you have, when your results say that for 2 crops, definitely it works. Are there any other?
Yeah, yeah. So because the crop yield prediction, yield data is not available for many crops, or the number of counties or the regions are very limited for some crop. That's why we couldn't perform this study on many more, crops. But I think this will work for all kind of crops because you need the bands data, mainly the bands which are, we have done this study also, which bands are better for crop prediction, crop yield prediction for some of the crops. So we found that there are, out of 12 bands, there are 6 7 bands which are more contributing towards the yield prediction. So those, I think, mm, eh, mainly in many crops they will work, and histogram will work until unless it is spatially, location is specific something, that pixel location matters. So in crop yield prediction, pixel location itself doesn't matter. You only need what is the value of the intensity for that band.
Got it. Yeah, I think that's all from my side. Thank you.
Any other
Yeah.
question?
The time series augmentation is interesting, ma'am. So we can usually take any augmentation when we expect that the outputs don't change, even if we distort the inputs, right? So why is it the case that the output uh, yield would be the same even if we reverse the time series?
So Aditya, your voice is breaking. So, but what I have understood is that you are asking that if we change something in time series, the output should not change.
Yes, ma'am. So
Yeah.
why is
So that's what. So in reverse, in text also you do forward, and you do reverse also. So if you have seen the BERT architecture, or I am not sure, GPT architecture, I guess that uses the reverse ordering also, reverse text. Not GPT. GPT is generative actually. I think BERT.
transformer? But yeah, it
Yeah,
makes
is so. So the output is, so the target we are keeping same. This is same time series. We are reading from the harvest towards sowing. So it will, the learning will be better. Though we
Okay.
are using bidirectional LSTM, but still it is better.
Okay. Okay.
So it is similar to, as you do in birth.
Okay. Yes. Okay. Okay. Essentially, the idea is from birth. Okay. Yeah. Yeah. That's the main idea.
Okay, then I
I
think.
think that's all from the audience. So,
Thank you
thanks
so
for the
much.
wonderful talk.
Yeah, thank you so much for patient listening. Thank you.
Yeah,
Yeah.
thank you.
Thank you.
So let's meet next week.
Yeah,
Same.
sure.
Yeah.
Yeah. See you.